Hey, hello, and welcome to the solutions here for exam number 2. Well, let's run through them. Hopefully you finished up the exam and it went well and you're feeling good about it, and maybe you have a few questions, but let's do a little self-grading, self-checking here. I'll start with the first one. I printed up the test here. It talks about the Golden Gate Bridge. It says how long it is, tells it's made out of steel. Then they gave you the expansion coefficient of steel and basically asks how much will the bridge grow between a cold night in winter at about 0 degrees Celsius to a hot summer day of about 40 degrees. That might be a little too much of a temperature spread for San Francisco, but maybe not. It's certainly within the realm of possibilities. And definitely in other areas. And so the engineers will have to, design for that. And so putting number 1 here, hopefully you remember that the change in length is equal to this coefficient, the thermal expansion of coefficient, times the original length, times the change in temperature. Now, I suppose it brings up 2 questions about the measurement of the original length. It doesn't really matter, and I guess I'll show you that to you, because I had a couple people email during the exam about this. But what do you mean by original length? And if the original length is then measured at 0 degrees, then this would be your calculation, because you would go from 0 up to 40, putting in your original length. If your original length was measured at, say, room temperature, 20 degrees, then we would have to say it shrinks, to get how small it is. At 0 degrees, it shrinks by that much, and I'll put just absolute value. Because then on the hot day, it would grow by 20 degrees. It would go 20 up to 40. So if the original length was really measured at 20 degrees, you would get this, which actually then simplifies to exactly the same thing. So it doesn't really matter whether we're talking about the original length measured at 20 degrees or 0 degrees, at least for this problem. There are some issues where that can come into play. So we do like to say what the original length is and what the temperature is. And this problem probably should have included that, because it can bring up questions in your mind. But for this particular problem, specifying the way it's specified, their original length doesn't really matter whether it was at 0 degrees, 20 degrees, 5 degrees, 4 degrees, whatever. Doesn't really matter, because we're not doing kind of this back and forth piece. Anyway, so to finish the problem then, I'll just use this one. So this would be 11 times 10 to the minus 6. The original length is the 2737 meters. And as we said, the increase in temperature is 40 degrees. So grabbing a calculator here, this would be 11 times 10 to the negative 6 times 2737 times 40. And about excuse me, about 1.20 meters then is how much bigger it would get. And that's always the challenge of building a bridge. All these pieces you are making are expanding or contracting. And in the process, making the bridge is a bit of a challenge. So, all right. So number 2 here says that we have 1 liter, and then gives the dimensions, although that's really not too important. I'll put it on the screen. But a 1 liter, a 10 centimeter by 10 centimeter by 10 centimeter, cube of ice at 0 degrees is inside an 11 liter strong fixed volume container with 5 moles of nitrogen gas at 100 degrees. So that would mean if the total space is 8 liters, 1 liter being taken up by the ice, we have 7 liters of room or space taken up by the gas. And so the gas fills all the available space to it, which in this case would be 7 liters, not 8 liters. It then asks how much ice melts. So obviously what's going to happen here is that we have a transfer of heat. So maybe in here is my container, and maybe in here I have this block of ice. And the warm gas then is going to be cooled by the ice, and of course then also melting the ice. Now, these type of problems always bring up the question about, is all the ice going to melt? And if it does, then it'll start to warm up and the final temperature will be above 0 degrees Celsius. But if all the ice does not melt, we still have some ice left over, then the final temperature is going to be 0 degrees. We're going to cool the nitrogen all the way down to 0, and then things are at thermal equilibrium, and no more ice will melt. So that's always a big question. And to be quite honest, I tried to give you a lot of ice, so it was pretty obvious that not all the ice would melt. Maybe it's worth kind of just saying, well, what if all the ice did melt? So we have 1,000 grams of ice, and it takes 330 joules to melt 1 gram. So it's going to take 333,000 joules in order to melt this whole block of ice. So that is the reason I picked ice, because it has this high latent heat, or latent heat of fusion, and this has a lot of mass, and that's just a lot. So hopefully it's beginning to look very obvious to you that, okay, this is not going to melt all the ice. It's not even going to be close. But of course, that's in a comparison to how much heat could be given to it. I mean, because obviously, if enough energy was given off by the cooling of the nitrogen, it could actually, melt. If there was enough hot nitrogen here, we could melt all this ice. So we might want to think about how much do we have, and it's a fixed volume type of calculation. So it made it very clear that we had 5 moles. And then, of course, they say it is nitrogen, and the key there is it was diatomic, and there's 5 degrees of freedom. So the molar specific heat would be 5/2 R. And if it did cool all the way down, it would be cooling down 100. So let's just ask this question. If it does cool down, all that energy would go to here. And if that is then less than this number up here, then all the ice did not melt. If it's more than that, then it would have melted all the ice before it got down to 0 and then started to warm up. So the final temperature would not be a 0. And you can see here this number is not even close. If I go 5 times 5/2 times R, which is 8.31 times 100, we're looking at just a little over 10,000. And so 10,387.5. So clearly not even close, not even in the hundreds of thousands, let alone 300,000. So again, just more evidence that we're not going to melt at all. So what that means then is we'll have the sum of the Q's equaling 0, and there'll be a Q1, I'll call that the energy going into the ice, and there'll be a Q2, that's the energy coming out of the nitrogen gas. And so this would be MLV, where M represents the amount of mass that melts. Which is a number that's smaller than the 1,000 up here, and that's what I'm trying to say. So we would send in the energy from the nitrogen as NCV, and then a fully decreasing 100 degrees from the warm gas to the 0 degrees. And of course, this number is what we just did up there. So this is 10,387.5. And all of that goes into, I guess I should have put a negative here. That's technically a negative. It's a decrease in temperature, which makes the math a little bit better. So when I move it to the other side, it's a plus 10,387.5. And then I'm left with this M times L. And so if I divide by the L, which is 333, This is going to give me the amount of mass that melts. So taking this 10,387.5 and dividing it by 333, I'm looking at about 31.2 grams. So again, not even close to 1,000. So I'll say it again. Hopefully the numbers were so big that it was obvious that not all the ice was going to melt. Try to make these first two pretty easy. We got some harder ones coming up here. But yeah, very clearly, it's not going to all melt. So we need to then figure out, well, then what does go into the ice? And so the stuff that goes into the ice is that mass, that M. How much did it melt? Hopefully you didn't put 1,000 there. This doesn't represent the mass of the whole piece of ice. This represents, the energy that goes into the ice. So it represents the amount of mass that melted. So the 31.2 is the answer for number 2. Okay, well, keeping that in mind and maybe moving on to number 3 here. 3 is kind of an extension of number 2. It says, what is the total change of entropy back in problem number 2? Okay, so the change of entropy, and maybe I'll just do the nitrogen gas first, would be an integral of dq dt. Okay, so the Q is the change in energy. And we have to integrate it, and this does make a little harder integral because the temperature does change. And so let me replace this Q with the N CV dt. So this is N CV dt over T, so that then the N and the CV, and then we just have an integral of dt over T, which is a natural log of final temperature over initial temperature. All right, so the nitrogen would be these 5 moles, and the molar specific heat, as we already said, at constant volume is the 5 degrees of freedom, so that's 5/2 R. And then the natural log, and we got the final temperature. Now that's 0 degrees Celsius, so I'm going to put in a final temperature of 273. Remember, they cooled all the way down to 0 degrees Celsius, to the ice temperature. And it started at 100 degrees, so that's 373 on the Kelvin scale. And so that number should come out negative, and sure enough, a natural log of less than 1 will be negative. And so this should tell us what the change of entropy of the nitrogen gas is. And I'm kind of expecting a negative number because it's cooling down. It's going to be less randomness. They're not going to be moving as fast. So there's a decrease in entropy for the nitrogen. Okay, and that number would be, looks like 5 times 5 over 2 times 8.31 times the natural log of 273 over 373. And so that is a decrease, a negative value of 32.4 joules Kelvin. And that's part of the problem. That's half of the problem. Because the other part of this is now, what is the change in entropy of the ice? And starting with the same integral, but recognizing that temperature is the same during the phase change, and this whole thing, the ice started at just that ice at 273 Kelvin and stayed there. So this formula for the entropy is a little different. This is the amount of heat that goes into the ice over T, the temperature. Now, since it goes in, that's positive, and so we're going to get a positive number here. Again, as we would expect, because the molecules are going from being locked into a crystal, kind of organized, and now turning into a liquid where they're just kind of all jumbling around on each other. So that is the increase in entropy. Okay. And jumping back and looking here at number 2, we did figure that number out. That goes in. It came out of the nitrogen and went into the ice. So it was this 10,387 that went in. So 10,387.5 joules went into the ice at, of course, a temperature T of 273 Kelvin. So grabbing a calculator here, 10,387.5 divided by 273 makes 38 points, and it looks like it rounds, just barely down, 38.0 joule Kelvin. And then to get the total, we would combine those two. So 38.0 minus the 32.4 leaves me with a positive 5.65. Well, I just can't really justify that decimal place there. Yeah. So with the number of decimal places I picked. So 5.6 joule Kelvin. And so, of course, definitely a positive. That was our second law of thermodynamics, that if you add up all the entropy changes, you got to get a number that's greater than or equal to 0. At best, it's equal to 0. Maybe I shouldn't say best, because that kind of depends in your definition on what's good and what's bad. And but the entropy is definitely an increase. So there's more increase in entropy than there is decrease in entropy. So every process needs to have at least an equal amount of increase and decrease, or more increase than decrease. So it's a kind of one of our different laws of nature, in the sense that it is not an equality, it's an inequality. All right, so anyways, there's the problem, and there's the answer. So now we can move on to number 4. And number 4, if I put it here in the screen, says I have a monoatomic gas and is compressed at constant temperature from A to T. So from A to T in the PV diagram is right there. And so that's temperature equal a constant. Okay. The gas is then warmed at constant volume from T to O. So from here to here, V equals I'll just put a C, a constant. Okay. And then third, the gas is expanded. Okay, so we're going to go this way. Expand, bigger. Under the condition of constant pressure, so it's a flat level line. So P equals a constant. And then finally, the gas is expanded adiabatically back to its original state, M. And so the adiabatic has this curve that's steeper and looks a little bit like the constant temperature one, but it's not a constant temperature. It's a constant heat. It's no heat goes in and out, but work will go in or out, and in this case out, because we're getting bigger. So then internal energy will go down. But this question's really not asking about the energy, so I guess I shouldn't have brought that up. But anyways, back fill in the missing pieces here. Okay. So maybe the first thing I would do is kind of look for things that, maybe are the same. That are easy to pick out, like constant temperature. So from A to T, do we know the temperature? Well, we know it at A, so at T it must also be 300. So I would do that first. Put in what I do know. All right, constant temperature. Likewise, right here, from T to O, it's constant volume. So if I go T and O and I look at the volume, I do know the volume at O, so that means I also know it at T. Okay. Now from O to M is constant pressure, so here's O and M, and constant pressure means that they would be the same at both O and M, and I know it at O, so I can write it down at M. So that's what I do first. I just find out the easy ones, the ones that are constant. The adiabatic doesn't have any of these three constants. It has the heat energy exchanged is equal to 0, so nothing I can put in this chart. The energy chart, that would be different, but in this chart, nothing I can really put there. Okay, so with that in mind, I'm kind of going, okay, now what? And I guess maybe the first thing to go to my mind might be, now, remember PV equals to nRT. And so that means if I know any three of these four, P, V, N, and T, I always know R, that's a constant, I can get the other one. But sadly, nowhere in this problem and nowhere in this chart does it say how many moles I have. So I'm pretty sure that's why I got a number of emails during the test at this time going, hey, how many moles is there? It doesn't say. Because you can see if you knew the number of moles, then you would have the other two and you can get that third one. And you could do that not only in the first row, you could do that in the second row, you could do that in the third row, and you could do that in the fourth row. But sadly, maybe this is where it gets a little harder. Well, we don't have that. So that makes me think about maybe something a little bit different, and that is we know something about the adiabatic. And that adiabatic says if you know pressure and volume. Well, let's try that. Let's see, the adiabatic is connecting the A to the M. So if this is the pressure at A and volume at A, and then this would be the pressure at M and the volume at M. And so if I look at that, that would be, these four would be those two and those two. Well, that doesn't quite do it. But also remember with this, we could switch any of the pressures to temperature and then just have temperature and volume. Or we could switch the volume into temperature. So then we would have pressure and temperature. So it's not just these two, it's any two. And so if you look at A and M, you'll notice right here there is a V and a T, and in M there is a T but not a V. And so that's three of the four. So I would really want to do this adiabatic with volume and temperature. So I'm going to replace pressure with nRT over V. I'll do it here too. nRT over V. And you'll get an equation that you might have already memorized. The N and the R cancel off. You get T and you get V to the gamma minus 1 is equal to T times V to the gamma minus 1. And so there's a connection between the temperatures and the volume. And so if you know any three of these, you can get the fourth. And we do. If we call this A and A, we know both the temperature and the volume of A. And then we would call this M and M, and we do know the temperature at M is 450. This then would be the volume at M that I'd like to find. Now, a big key to the problem right here is monoatomic, since gamma is the ratio of the molar specific heat at constant pressure to constant volume, and the constant volume is related to the degrees of freedom. This would be 3/2 R, which would make this 5/2 R once we added R to it. The half and the R would cancel off, and you would have 5/3. So gamma is 5/3 for this problem. Okay, so I can then say over here, gamma minus 1 would be 2/3. Because if I have 5/3 and I subtract a 1, that's 3/3. I'm left with 2/3. And the same thing about A over here. This would then be 300. And then this would be the volume. I'll put a 20. I'll just do it in liters. And then it to the 2/3 power. So, grabbing a calculator here, I'm going to say 300 times 20 raised to a power of 2/3. Then that divided by 450. And maybe I'll do an intermediate step. That would be volume to the 2/3 is 4.91. So now, if I raise both sides to a power of 3/2, I would get, just volume. And this looks like then a 10.9. So 10.9. Nice. Now, that really kind of opens some really nice things, because remember we had said earlier on with this that if I knew the pressure, volume, and temperature, and I now have it on the bottom row, I can get the number of moles. And if I know that, then I can use it to fill in these other three, because then I would have all but one in each of the lines. So, grabbing my calculator, I will take a pressure of 686, 1, 2, 3. So that's the pressure in pascals. Taking the volume to be 0.0109. So there's the P and the V in units of pascals and cubic meters. Divided by the R, 8.31, divided by a temperature of 450, and that's 2.00 moles. Okay, so coming up to this first line, pressure then would be nRT over V. And I can use that in line 1, and for that matter, line 2 here. Okay, so let me take the number of moles, which is 2, or I'll just use the number that's already in my calculator, times R, 8.31, times the temperature, that's 300, then divide it by, there we go, kind of got off there, then divide by, let's see, this is nRT, okay, right here. Then divide by the volume, and 0.02 would give me a pressure of 249,246. I'll just go 249.2. Now I can redo all this calculation, but it's not, I don't think, necessary. If you look at the next line, the nRT is going to be the same, except, I mean, the top, the nRT is the same. And instead of dividing by a 20, I'll be dividing by a 10. And so that'd make that one twice as big. So this would be 498.4, or the extra carries over, and I'll put 0.5. And so there would be the pressure when I, go from a change of constant temperature. This is referred to right here as Boyle's law, where if you cut the volume in half, the pressure doubles. Now, the last one to do is O, where we can get the temperature. And then again, we can just write here that temperature would be pressure times volume divided by nR. So at O, I'll go pressure, which is the 686,000 times 0.01, divided by the N, which is 2, and divided by the R, and get a temperature of about 412.8. How about we do that? Or 13 Kelvin. Okay, so a little more work, a little bit more time consuming, obviously, but really relied on that adiabatic, as well as the ideal gas law and recognizing it's monoatomic. But maybe the key is that connection between A and M. All right, well then finally moving into the last problem, and deliberately trying to give you the same cycle so you didn't have to spend too much brain power on rethinking these processes. This one, although there are some changes here, it says it's the same cycle as the last problem, okay, but now we're going to have a diatomic gas. All right, so let me just put that up here. Diatomic means that our CV is going to have 5 degrees of freedom. And so our CP, being 1R bigger, is going to be then this 7/2 R. And that's going to mean gamma, which is the CP over the CV, will be the 7/5 because the 1/2 and the R will cancel off. And so keep in mind then for this question, we aren't quite getting the same numbers as we, got over here because we have a different type of gas. Oh, and also we have a different amount too. So not only is it diatomic, but we have a different amount. Although the nice thing is they actually tell us that amount. So the number of moles is 4.25. So maybe that would explain why I didn't get to that question during the test. Nobody asked me about how many moles were in number 5, but a lot of people asked, can we assume the number of moles in number 4? Did I make a typo and no to both of those? We can figure it out. It's 2 moles. And we did. Okay. All right. So this problem is different. We're asked to fill in the energies as we go back and forth. And of course, to do those, we probably need some numbers from what their temperatures and their pressures and their volumes are. So you may fill in some of these if you want, but I actually did give you the numbers that were the minimum that you could do it. So you don't need to really find any numbers up here that to do these. It kind of depends on how you do them. So let's just work through them and see what ones we might want to calculate up here, if any, but let's fill in these. And this is my same thinking that, like back on number 4, go for the easy ones first, the zeros. All right, so from H to E, there's no temperature change. That means dE is equal to 0. Okay. Now, from E to A, there's no volume change. So that means the work is 0. Now, the A to T is constant pressure. None of these are 0. Okay. And then the T to the H is adiabatic, and that's the definition of adiabatic, no heat. So that would be my go-to place to start. I would just say, okay, let's put in all the ones I know at 0. And keeping in mind that these two, the work and the heat, add together to give me the delta E. So if I know any 2 across here, I can get the third, which doesn't help me so far. Also keep in mind it's a closed cycle so that all 4 of these added together is 0. We'll see if that helps. And then we know these would then be equal and opposite, and that may be helpful, but I don't think so. All right. So I've got all the zeros, and the thing I like to do are the state functions, because the state functions have the same equation regardless of the process. And so this is the equation we proved for it works at constant volume, but being a state function, we could then extend that to say it works for constant pressure, it works for constant temperature, and it works also for the adiabatic process. So let me just use that, and especially, not only is it a state function, but it involves change in temperature, and what's given are temperatures. So I really like the sign of that. Let's just go through and get these 3 here. All right, so from E to A, let me do that number. And so grabbing my calculator, the N is the 4 1/4 moles. The CV, as we said a little while ago, is the 5/2 times R. And actually, let me just hit enter because I think I'm going to want that number a lot. All right, so that's 88.29. Then I want to multiply by the change in temperature from E to A. So that would be the temperature at A, 340, minus the temperature at E, which is 300. And this comes out then to be A plus 3532 joules. Let me come back and grab that 88. That's the N and the CV multiplied together. And let me then just say times a change in temperature. Now, in this case, we're going from A to T. So T is where we end, 425 minus 340. And so this would be a 7,505. Now I've got two options here. These 4 have to add to 0, so I could just add these 3 and then do the opposite of it. On the other hand, going and doing this one more time wouldn't be bad, especially since it's in my calculator. So I'm just going to do that, re-enter, and scroll back here and go T to H. So H here is 300, and the T is the 425. So this is a negative 11,037. And maybe just to check, you can see that the 2 and the 5 make a 7. 3, 10, carry 1, 10, 11. Perfect. Put a negative in front of it. And so, yeah, this is the opposite of these two added together. So all 4 of these added together is a 0. So, making me feel pretty good about those. Now, that's really helpful as I scan across, because remember, if we know any 2 across the row, we know the third. So, like in the second row here, with that 0, we know this one must be the 35, 32. Because that's plus that, it's got to equal that. Now, also in this fourth row here, this plus this has to equal that. So this must be a negative 11,037. Okay. All right, well, I think that's as far as I can really go with the easy ones, the being 0 and the state function. And now I need to look more at some of these other ones. And Q might be a good one because we do have this set of equations that Q at constant volume is N CV delta T, and Q at constant pressure is NCP delta T. Now, the constant volume was the E to the A right here. And we already finished that row, so I guess I don't need that one. I've got it. But the A to the T right here at constant pressure might be perfect for that one. So let me fill that one out. The N is the 4 1/4. The CP we put up here as 7/2 times 8.31. And now we can go the change in temperature. So T minus A. So that would be 425 minus 340. And I get, looks like 10,507. Now, we'll be back to the place where we said this plus this has got to equal that. So this right here, this work on the third row must be a negative number. Because we start with 10,000, we need to add a negative number to bring it down to 7,500. So I'll calculate that in just a second, but I just wanted to kind of examine the negative. The negative means it would be doing work on the environment. A to T means it would be getting bigger. Yep, A to T is it's getting bigger. Okay, so kind of like the signs of that. So why don't I just put in my 7,505 and then subtract 10,507, and we get a negative 3,002. Okay. And now maybe we get to the last and maybe even the hardest, depending on if you see it or not. But the first one, the a to the e at constant temperature, can't really do anything with heat on it. We didn't do anything, but we did do an equation for work. So let's do that one, which would give us that one also, and we'll be done. And if you remember the work being minus the integral of p dv, and putting in place of p nRT over v dv, and since it's a constant temperature process, you can pull out the n, the r, and the t, and then just have an integral of dv over v, which is the natural log of final volume over initial volume. Okay, and that would be the equation for the work. So let me put that in here. And doesn't have temperature in it, but it has the ratio of the volumes, and those are the other two things given in that table. So we don't really need to find the other things in this table. Kind of nice. But we could just as well, especially since it's like the last problem, we know the A and the T are connected. These two would then connect here. Although we have N, so we could get that and that real easy too, because we know that, you know, the N. And then, of course, once we got to E, E to A is constant volume, so we would know that would be a 4, so we can get that real quick. And then A to T is constant pressure. Oh, so we can get that. And so we don't have to even do the adiabatic process here because the number of moles are given. It's pretty easy. Oh, but I digress. I shouldn't even be talking about those because well, that's all we need here. All right, so let's finish this and finish the test. And so let me put in the negative number of moles, which is negative 4.25. Let me put in the 8.31. Let me put in the constant temperature of 300. Let me put in the natural log of, and so from H to E, the final volume would be 4, the initial would be 12, and that's then going to come out to be a positive 11,640. Let's talk about the positive. That means we're doing work on it. That means we got to be squishing it, yeah. So H to E, we're squishing it, good. And then the final step is to realize that these two add up to 0. So this must be a negative 11,640. And we can even check by adding these and see if this number is the opposite of that. And this should come out positive, and that should come out to be equal in magnitude but negative, and it looks like it does. But I'll call it quits for now. So there's the exam. Hopefully that was helpful.